Hello and welcome to Lecture 2 of the Traveling Waves unit of Phys 1201. And in this lecture we're going to look at how we represent waves. And the focus of this lecture is going to be on two ways that we draw them, two types of graphs that we draw that we call history and snapshot graphs. Remember from last lecture that a wave as it's propagating through the medium doesn't change its shape, and that its shape is determined by the original disturbance. So with the long springs, you saw me wiggle the spring upward, and it caused an upward bump to propagate along the spring. And if I wiggled it downward, a downwards little trough would propagate along the spring. So let's now look at two ways that we represent waves. The first is called a snapshot graph. And it really is just like a snapshot. It is showing at an instant in time what the displacement is like at each point along the medium. But notice that means that it's showing how far the medium is displaced at each location. And so it really is just like what you would see if you were looking at the wave itself, or if you drew a picture of the wave. So a snapshot graph is not at all abstract. It's really very concrete. It's exactly what you would see looking at the wave, except that it may be rescaled for convenience. So here is an example of a snapshot graph, and note that it has to be specified as being at an instant in time. Now I've indicated a point on medium, so this is just a location. So again, thinking about the example of me sending waves down the long springs, think of this as a labeled point, just like the place where I had tied a string onto a coil of the long spring. So it's a piece of the medium that we're going to keep track of. And now we can draw the other kind of graph, which is a history of what happens at this point A. And so we call it a history graph. Now I haven't drawn this one. I've left these question marks here because what I'm now going to show is how you figure out the shape of the history graph from thinking about the snapshot graphs. So I have drawn one piece in. So if you look at the point A, the wave hasn't reached it yet. The wave is coming along from the left, and so it hasn't reached it yet. And we see there's nothing going on out here. And so we can infer that this point A has been sitting still for some time. And so that's what I've drawn. A zero displacement for these times. These are negative times, so times before t equals 0. Now, if we look a second later, I've drawn that the wave has traveled onward a little bit. And it's just reaching the point A. So the wave has traveled, but point A hasn't started moving yet, and so I've continued along the zero displacement line in the history graph. But now at t equals 2, note that point A is partway up this leading slope of the wave. And so I've drawn an upward piece on the history graph, because if you imagine the times between this time and this time, that point A would be gradually rising upward as the wave comes under it. And so a second later, it's now at this highest point at the top of this leading slope of the wave. Notice how the wave is moving along, but this point A is a piece of the medium. So it is not moving along, but it responds to the local displacements of the medium that are caused by the wave. And so this is now the story of what point A has done so far. It sat still, and then it went up slowly. Now it sits still for a moment as this flat piece of the top of this wave passes under it. So here it is sitting still at some positive displacement. And now there's a steep-sided back edge to this wave, and so in the next second, point A drops down more quickly. And we're basically done, except to say that now there's nothing going on out here, so as the wave travels on farther, point A is just going to sit still back at zero displacement, and we've finished this history graph. And just notice that the reasoning was all around picturing what's going on as the wave travels, and you get a sequence of different snapshot graphs. And note that a snapshot graph, every single snapshot graph, you have to specify what time this is a picture of the wave for. Whereas a history graph, you have to specify what piece of the medium it is a story of. If we instead chose a point farther out here, then it would have a history graph that's exactly the same shape, but the leading edge of the wave doesn't get there until later, and so the whole thing would be displaced to later times. Now, what I find most students get the most confused about is something which, if you recognize what's going on, is really very simple. And it's the difference between a snapshot graph is a picture just like a snapshot that you would take with a photograph. And so right is right and left is left. Duh. But, maybe not duh, because if you think about the same thing with a history graph, it's not like that. This is a time axis, and so right means later, and left means early. And if you think back and forth that way about these types of graphs, then you'll help yourself avoid getting confused about what they're talking about. Things going on over here in a history graph are things that happen early at the point you're drawing the history of. And then it's useful to note that any wave traveling along has a leading edge and a trailing edge. Because this wave is traveling to the right edge of the wave is its leading edge. Notice that the history graph is the same shape as the snapshot graph, except it's flipped right to left. They each have a shallow slope and a steep slope, but in one, the steep slope is on the right, and in the other, it's on the left. But it's not always that way. We'll see a case in a moment where they're not flipped right to left. And the thing to realize is that the leading edge is always the same shape as the early part of the history graph, because by definition, wherever you look on the medium, the first part of the wave to reach there will be the leading edge. And so the history graph ends up having its early part, well, early is always the left, having the same shape as the leading edge on the snapshot. But the leading edge could be on either side on the snapshot because the wave could be traveling in either direction. Let's do another. For two reasons. First of all, I want to show you a different case. Second of all, I want to show you that you don't have to draw a big sequence of snapshot graphs, although that's often good for practice. And thirdly, I want to do one with all numbers in. So here's a snapshot graph of some wave, and this is the snapshot at t equals 2 seconds. And note that this wave is going left. And we're going to draw a history graph for the position x equals 3 meters. And just note that the scales on the axes of this snapshot are different. This is quite common because often you have waves traveling down, say, strings, where the amplitude of the wave may only be a few centimeters, but the string is many meters long and the length of the wave is many meters long. And so you often get this difference of scales. Now, this is a history graph, so the first thing to recognize is you're telling the story of a point, and so this is going to be a time axis. And before you start trying to draw it, it's good just to sketch roughly what it should look like. So the main thing is just to work out which way around it'll be turned. So our displacement versus time graph, if you think about any point, now the point we're interested in is x equals 3. But no matter what point you think about, recognize that the leading edge of the wave is this piece. And so whenever the wave gets to a place, the first thing that happens to a piece of this string, or whatever it is, as the wave arrives, is it goes down as this piece arrives at the location you're looking at. And then it's going to go up, and then it's going to slowly subside back to zero displacement. So we know that our history graph is going to look something like this. And now we just have to get it scaled right. So we're looking at the history of x equals 3. And this is a snapshot at t equals 2. So the first thing to say is, well, when did the leading edge of this wave arrive at this location? We see that it's already past it. When did it get there? Well, the wave is moving 1 meter per second, and the leading edge is a meter past the location we're looking at. So that leading edge must have passed x equals 3 a second ago. And so that means at t equals 1 second. So we can start putting on a scale. We know 1 second is going to be important because that's when the first action happens at the location we're looking at. And so what we just saw is that the first time anything happens at this location is a second before this picture, and so that's at t equals 1. And so at t equals 1, that point must start going down. And it's going to take a second for this downward slope to pass by there. So we know already that at t equals 2, the point we're interested in is at its maximum downward displacement, because that's what this graph is showing us. And so there we go. That's the first piece of our graph. We know nothing happened before that. And now we can just fill in the rest. The rest is going to be just the same shape as the snapshot of the graph itself. And so you see, in this case, the history graph isn't flipped right to left relative to the snapshot. And we reasoned that out just by thinking about which side of this wave is the leading edge, because the leading edge has to match what happens early in the history graph. So I'll just comment, this is going from a snapshot graph to a history graph. Going the other way from a history graph to a snapshot graph for some reason is harder, and we'll practice doing that in class. Up until now, we've been talking about waves that are these funny pulses, and often with, weird straight edge sides and so on. And that's partly to make them easier to think about. But in fact, in electronics and various other areas, we actually often do see waves that look like this. But now let's move on to by far the most common type of wave that you encounter, and those are sinusoidal waves, which are probably more like what you associate with waves. So remember that the shape of the history graph and the snapshot graph are always the same, and this tells us something very important. What if the disturbance producing the wave is simple harmonic oscillations? Then that means the location of the disturbance will have a sinusoidal history graph, and by extension that means every other piece of the medium will also have a history graph that's sinusoidal. And since the history and snapshot graphs have the same shape, that means the snapshot graph will also be sinusoidal. If you look at the wave, it will be the shape of a sinusoid. So anytime a piece of the medium is disturbed in simple harmonic oscillations, you wind up with a wave on the medium that is sinusoidal on shape. Here's our snapshot, here's our history, both sinusoids. So this is a very important case. It's very common, and so we're going to spend the entirety of the next lecture on sinusoidal waves.